Hi, everybody. Welcome to my organic synthesis presentation project. I'll be discussing the preparation of a donor acceptor Stenhouse adduct, or DASA for short. So let's get started with a little introduction about DASA. So DASAs are an emerging class of negatively photochromic photoswitches. They include properties such as visible light activation, high extinction coefficient, negative photochromicity, and more. They're also used for drug release, phase transfer, programmable adhesion, photothermically controlled flow, and amine or heat sensing. Now let's move on to the overall reaction. So this is the general reaction, and it's combined into two parts. For the first part, Meldrum's acid is combined with furfural and is reacted with water and temperature to create this product. This product is then reacted with THF and diethylamine to form the final DASA solution. We will go more into the reaction later, but for now, let's talk more about the scale and optimization of this procedure. This experiment is best optimized in an organic laboratory setting as it uses hazardous chemicals that may be dangerous in some sort of way. Therefore, it's important that all chemists that's undergoing this experiment has underwent proper training with experimental organic chemistry. The chemical used in this experiment, such as Meldrum's acid and diethylamine, were purchased without further purification. So this experiment could have some high expense depending on the price of the chemicals obtained. Other than that, the equipment used within this experiment seems to be the typical equipment you would find in an organic laboratory setting, so it could be used on a normal or large size scale amongst organic laboratories, depending on the equipment used and the chemicals received. Now let's take a moment to talk about the checking process. Having been published in the Organic Synthesis Journal, this article has been checked for reproducibility from a member of the board of the editors, two members in fact, being Feng Ping and Kevin Campos. The checkers contributed to the reaction by providing a picture of the reaction vessel after heating it for 2 hours. They also checked the reaction by utilizing furfural without purification compared to distilled furfural that was used within the experiments. Other than that, they didn't appear to make any other comments for this procedure. Now let's move on to the reaction apparatus. This experiment utilizes a 500 milliliter round bottom flask with a single neck. The neck is connected to an air condenser with a rubber septum fitted with a needle outlet. A Buchner funnel with a filter is used to filter the solution to a 500 milliliter sidearm flask using vacuum filtration. The reagents and starting materials include Meldrum's acid and furfural. The limited reagent is Meldrum's acid and the excess reagent is furfural. Furfural and the excess reagent is needed to determine the theoretical yield. Besides the standard safety procedures for work with chemicals, no special precautions were required for these starting materials. And these materials were utilized without further purification, so no further purification were needed for these reagents. So, as mentioned earlier, this procedure runs two parts. The first part involves reacting Meldrum's acid with furfural to form a product. This product is then reacted to form the final DASA, making the order of addition important. This procedure is monitored by its physical properties, or visuals. DASA has visible light activation properties, so we can expect things such as color changing. Let's move on to the first part of the experiment. First, an oven-dried 500 milliliter round-bottom flask is equipped with an egg-shaped Teflon-coated magnetic stir bar that's connected to an air condenser that is capped with a rubber septum, which is fitted with a needle outlet open to the atmosphere. 15.1 grams of Meldrum's acid is charged into this flask, 300 milliliters of water is added to the flask, and it's heated in an oil bath to around 60 degrees Fahrenheit. sorry, 60 degrees Celsius. 9.6 grams of furfural is then added, and the reaction mixture is stirred at 60 degrees Celsius for around 2 hours. Here, in the pictures, you could see that the solution first turns yellow upon the addition of furfural. Then a yellow precipitate forms before turning black with additional yellow precipitate forming, which you could see in the A and B pictures of here. After around 2 hours, the solution is left to cool to room temperature and then filtered through a Buchner funnel, which is 6.5 centimeters in diameter, equipped with a filter into a 500 milliliter sidearm flask. The off-colored yellow solid is then dissolved in 100 milliliters of ethyl acetate hexanes. The solution is then filtered through a vacuum filtration adapter, plugged with Conan and charged with silica gel. Using ethyl acetates as the mobile phase, the yellow band of material is collected from the silica gel column and concentrated at room temperature by rotary evaporation, and then add 0.05 mmHg to provide the product as a yellow solid, which you could see here in the bottom picture. From the solution that was made from part 1, it's then charged into an oven-dried 100 milliliter round-bottom flask with an egg-shaped Teflon-coated magnetic stir bar and is capped with a rubber spectrum. 10 milliliters of THF is then added to the solvent as well. The mixture is then stirred in a cold water bath, and 4.7 milliliters of diethylamine is added dropwise using a syringe for over 20 minutes. Upon adding the diethylamine to the solution turns from dark yellow to bright pink and then dark violet, which you could see in the picture to the right. After the diethylamine is completely added to the solution, it's then stirred at 22 degrees Celsius for 20 minutes. For the reaction workup, diethyl ether, 20 milliliters of it, is added to the solution, and it's filtered over a Buchner funnel, which is 6.5 centimeters in diameter, and it's equipped with a filter at room temperature. The solid is then washed with diethyl ether, 20 milliliters of it, and dried at 0.005 mmHg to provide the product as a violet solid. So as you can see, this reaction is purified through the purification process called distillation. This involves heating and cooling the mixtures to purify it, and then it forms the final products. The authors used NMR spectroscopy to prove they had the right material. That's their proof of purity. They also provided a second reaction for both products on an identical scale that yielded 86% for the first product and 71% of the second product purity, respectively. And as you could see on the bottom, these two pictures, the one on the left is for the product 1, and the one on the right is for the DASA product. These are the NMR spectroscopy results. The article mentions safety procedures throughout the experiment and constantly reminds chemists that all chemical materials should be handled using procedures described in the prudent practices in the laboratory. Before performing this reaction, a thorough risk assessment should be carried out, which includes a review of the potential hazards associated with each chemical and experimental operation on the scale that is planned for the procedure. This reaction holds chemical hazards and can be dangerous if it's mishandled. If proper procedures and guidelines are followed, this lab would be less dangerous, and it would not be significantly more dangerous than other labs. So it's always important to make sure that these dangerous materials are handled correctly. So that was the procedure for the preparation of DASA. But it's interesting to note that originally DASA photochromes were based on dialkylamine donors and acceptors derived from either Meldrum's acid or barbituric acid. Over here, we can see the modular approach towards Stenhouse salts and donor-acceptor Stenhouse adducts. The authors from this article propose further experiments with the intention of enhancing switching properties and control of the dark equilibrium, which you could see over here. Finally, from the experiment that was done, the experiment proposed the photo switching mechanism of DASA, which you could see in this module over here. This is a complex photo switching mechanism, but it basically involves um, the easy isomerization around the alpha bond next to the hydroxy group from this to this, and then subsequently a thermal bonds rotation. It sets up a determining for electrocyclization, forming the first colorless closed form isolator from this one to here. Then the closed form then goes an orbital inversion on the amine from here to here, followed by a bond reaction and slash or a proton transfer to result in either a natural or Zwitzer-Teonic closed form. So here's a little bit about the authors of this experiment. Dr. Frederick Stricker, Dr. Julie Peterson, and Dr. Javier Reid de Alanis. They are all from the University of California, Santa Barbara. And the checker, Dr. Feng Peng, works with Merck and is from Columbia University. And here's the citation, and that is the end of my presentation. Thank you all for listening. Hope you have a great day.